ball here. That's a cross. With arrows.
Yeah, it's graph paper.
Can you give me some?
Okay.
If it was graph paper, it'd have a bunch of lines. And it'd be on the paper, not
Oh, if only I could draw that much.
Hey, Matt. How's playing with balls?
You want both or one?
He's been getting a mile of laughs out of the "you're still playing with balls" over there, so because you were playing pool.
Yeah, you make fun of local.
I know it's
Like
odd.
lacrosse, football, basketball, baseball.
Yeah, but there's multiple balls in that one.
Anyway, all right. How'd the last assignment go?
Good.
Oh, I tell you, it's quiet around here. Okay, 4.1 wasn't that big of a deal of an assignment. If you guys have any questions about it, obviously I'd love to talk about it and so on. But in the meantime, we're moving on to section 4.2, which is something that I think is really cool. What they want us to notice here is we're working with functions. Functions that can be surprisingly easy to draw, but surprisingly complicated to actually know what the values really are. I'm going to try to move this over a little bit farther here, just so we can see better. See, for example here, let's say this is a graph of y equals the square root of x.
No, I hate that graph.
You hate that graph. Why?
I'm just joking.
Okay, good. All right, here's the deal. We all talk big that we know exactly what that looks like and so on, but good luck actually finding the square root of 9.1. I mean, if you actually had to sit down with a piece of paper on a test and find the square root of 9.1, good luck with that. It's hard. Okay? The truth of the matter is, tons of equations that we work with are actually really hard to come up with a value of. I mean, what in the world is the sine of 59 degrees? Or whatever. You know, you plug it into your calculator, but it's just there. But actually sitting down with a piece of paper or something and figuring out what it is really hard. And the book is going to help us find a way of coming up with estimates of these sorts of values that turn out to be really good and turn out to involve calculus. What the book wants us to notice is that when you have a function that's something complicated, like this one I have up here for the square root of y is in square root of x, I mean, it's some curve. You okay?
Yeah, I just found that great news.
Okay. We'll wait with it, okay?
Good.
Alright. But here's the deal. Any little piece of this function right here, like if you could look at it with a magnifying glass, isn't really all that complicated at all. If you could just take a look at this little piece of a function right here and zoom in on it with a magnifying glass, that's pretty much just a line. I mean, no matter how wild and crazy the function is, here I'm just going to draw something else. So here's some crazy function. No matter how crazy the function is, if you zoom in on just a little piece of it, and look, it's pretty much just a line. It's not a line, it's curved somewhat, but it is pretty damn close to a line. And so the book is going to give us a way to come up with a linear approximation to some complicated function that admittedly won't work very far, but, like very far up and down the x-axis, but over a little area, it's going to be just fine. It's going to be pretty damn close to the right answer. So we need to be able to come up with ways to say, hey, if I'm talking about something, here's a value of x. Let's say we're at this place, x equals a. And I want to know the value of this nifty green function here, my y equals square root of x, someplace nearby, like at this spot right here, at some new place x. What I really just want is some kind of estimate of what the right answer is. See, like for example, if I'm trying to figure out the square root of 9.1, that's awfully darn close to the square root of 9, which I know because I've passed second grade math, right? I mean, we know that's going to be 3. So I'm close to there. Like if x was equal to not, like x is equal to 9 right here, I should be able to come up with a really good estimate for x equals 9.1. Because it's just going to be the slope of, it's just going to be this linear approximation. It's not going to work very good the farther I get away from our original point that we could work with, that we knew the answer to. But it's going to be pretty darn close. Now your book doesn't actually take very much time to try to derive this or something like that, a point for which I am grateful. Because it just says, look, it's going to be y is equal to, and I use different notation than we did in meteorology, so let me make sure I'm clear about this here. It's going to be f of a, now they're using pluses or minus, how do they define the signs here? Plus f prime a, plus f prime of a, times x minus a. This is going to be a linear approximation to your original, more complicated function. Near the value x equals a, this will give you a value y that's close to the correct value. Let me show you how this works. For example, for this function that we had here, where y was equal to the square root of x, or x to the 1/2 power, that's our f of x. What's its derivative? 1/2 x to the negative 1/2 power. Remember, we pulled this down in front, x to the, and then we subtracted 1 from the power. That's 1/2 times 1 over square root of x. So, our linear approximation will be y is equal to, okay, we're doing this near the place a is 3. We are talking about places on the x-axis close to 3. So, it's f of 3, not a, I did this wrong. A is 9. Sorry, I'm thinking this wrong here. We're at 9. So f of 9 plus f prime of 9 times the quantity x minus 9. We're near this location x equals a. Alright, f of 9. F of x is equal to the square root of x, so this is 3 plus, this thing here, 1/9 times 1/2 is 1/18 times the quantity x minus 9.
It's the square root of x. So it'll be 3.
Oh, you're right, that's 3, sorry. So this is 3, so you're right. I was thinking that there wasn't an 18 in this problem. I was wondering was I had done wrong. So that's a 9. So this is a graph of a line. I mean, if we rearrange this, we could get this in terms of a slope and a y-intercept, and it would be this thing. And this new equation, y equals this thing, is a straight line that it looks a whole lot like our complicated graph close to the value x equals a, or x equals 9 in this case. And in fact, in the book, they go through an effort where they actually do this here. So let me give you, let me go ahead and do that one right here. Somebody was looking at that. Did you? Here. Okay, so this is example 4.5 in your book on page 355, if you care.
So wait, the f prime
Of 9. So f prime is this thing right here. 1/2 times 1 over the square root of x. So we plug 9 in here. That's square root of x is 3. So it's 1/2 times 1/3 or 1/6.
Alright, just make
Yep.
sure there's,
So for example, so this thing that I have circled here, this is your linear approximation. So for example, if we wanted to come up with an estimate of this thing, the square root of 9.1, we could plug this 9.1 in for x. Y would be equal to 3 plus 1/6 times 9.1 minus 9. Which would be, I'm going to scooch this over a little bit because I can't quite get the whole board in focus at the same time. Okay. So that is 3 plus 1/6 times 1/10, or 3 plus 1/60th. All right. in the trig class, I learned to talk to my calculator, because then if I'm just up there going tap, 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 you don't know what I'm doing, right? So this way, when I talk to my calculator,
You can talk to your calculator.
what is 3 plus 1 over 60?
The answer is approximately 3.017.
Right? That is our estimate. Just out of curiosity, I don't know if the Google.
It's 3.01.
What is the square root of 9.1?
Square root of 9.1 is approximately 3.017.
Hey, they're pretty darn close to the within rounding. Neat, right? We did a little trick. Figuring out, I don't know, even want to know what the Google just did to actually do this math. Right? I mean, behind the scenes, what crazy voodoo actually had to happen to find out the square root of 9.1? Right? But we were able to do it using this approximation, pretty straightforward. Let's do another example. How about sine? I'm just making a problem up here. How about, I'm just going to look at something real quick in the Calc textbook. Hold on. I did the Calc textbook, the trig textbook, because I want to make sure I've used one that works out well.
You could find the actual answer though if you took on the derivative and then plugged in the actual value that you're looking for, right?
How?
Isn't the derivative just slope?
Yeah.
And if you plug in the number, then you find this, I guess you find the y.
Yeah, hold on just a second here. Cosine of, let's try another one. All right, so I think this is actually one that's actually related to one that's in your book. Let me just see if it's the same one. All right, yeah, let's actually do 4.6. I was going to make a slightly different problem, but let's just do 4.6 in the book. It says, you find the linear approximation to f of x equals sine of x. So f of x equals sine of x. And they're saying find the linear approximation at the value x equals 60 degrees and use it to find the value of the sine of 62 degrees. So what they're saying here is we can make a graph of the sine. And it's a fairly complicated thing. I don't even want to know what all your calculator or whatever has to do to find the sine of 62 degrees. It's a fairly complicated thing. Certainly not something you and I could do on paper. But we can come up with a pretty good approximation with it because it's somewhere near here where A equals 60 degrees. And in this region here, there's a straight line that's a really good match for what the sine is doing. No matter how crazy your function is, if you zoom in close enough, it starts looking like a straight line. So, we're going to use our idea here that we should be able to come up with some kind of linear approximation. It's plus, right?
Yeah.
Yeah. We do this in a slightly different notation in meteorology, so I need to make sure I do this carefully. So we are somewhere near where A was equal to 60 degrees. So our linear approximation is going to be f of 60 degrees plus f prime of 60 degrees times x minus 60 degrees. That's a linear equation. It will make a graph of a line. Let's see, f of 60, the sine of 60. I always have to look at my unit circle because I'm scared of it. The sine of 60 is square root of 3 over 2. Plus f prime. Okay, if f is equal to the sine of x, then f prime is equal to cosine of x. Alright, so the cosine of 60. It's 1/2, I think. Again, I always like to check just to be sure. 1/2 times x minus 60 degrees. That's a linear equation. I mean, with a little rearranging, we could have this mx plus b. Right? It's a linear equation. It's the graph of that little green dotted line I just drew up here. So this is what it was saying. So find the linear approximation. That's this thing. Then it said use that to figure out the value of f of x. Am I right so far, by the way? I think I am.
Yeah.
Yeah, they're using it in radians rather than degrees. But I don't think that's going to hurt anything we're doing here. You know what? Let's actually do it in radians. So let's take that 16 degrees out of here, and let's change that to 60 is pi over 3, isn't it? Yeah. Let's change it to radians, just to keep everything so that we're not playing games with the units. So we would need to change 62 to radians. 62 degrees is a certain number of radians. What is 62 degrees converted to radians?
62 degrees equals 1.082 radians.
1.082 radians. Alright, so what is pi divided by 3?
The answer is approximately 1.047.
Close enough. Alright, so our answer here is going to be, so the sine of 62 degrees is going to be well approximated by the square root of 3 over 2 plus 1/2 times the difference between 62 degrees in radians and pi over 3 in radians. What is 1.082 minus 1.047? What is 1.082 minus 1.047? That's not liking me very much. What is this going to be? 3 to 50, and then 32. Is this 0.035, yeah? Times 1/2. Square root of 3 over 2. Like that. What is the square root of 3 divided by 2?
The answer is approximately 0.866.
No, it's not letting me at all. All right, I'm having my calculator's kicking me up. But you do the math on this. Well, let's look at the answer on in there instead, because my calculator's in the wrong mode now. All right, so you look on page 357, and you will get that the linear approximation is let's see here. Yeah, so right there on page 357, they actually go through the whole business, and they end up with that the sine of 62 is about 0.88348. Hi.
Hey, I'm the only one here today, so
Do you need
just
help?
you and me. No. I was just letting you know.
Okay.
If you need anything, I'm the only one here. So.
Okay. I wasn't sure if you needed help at buses or something like that then.
No, none of you guys. No, there's nobody here. There's literally nobody here but
Okay.
these guys.
Do you know if I'm supposed to come tomorrow or not? I have a message out to Wendy, but I haven't heard back.
Tomorrow morning.
Because I only have 3, I think.
No. Yeah, seniors. Yeah, no, you don't have to come tomorrow.
Okay.
Why are there so many people going tomorrow?
That's
SATs.
taking SAT. That's new back in the home
free.
schools.
Yeah.
And
State's
today's
paying for it.
Lucky suckers.
All right.
No, you don't have to come tomorrow.
Okay.
She told you that, didn't she?
Nobody told me anything yet.
What? I would assume, I'll text her.
Okay.
Right now,
I've sent her an email, so I don't know. Maybe she's written back while I've been
That's
here.
bull crap. I want my $50 back
Oh my gosh.
for taking that SAT.
Oh my
I need
gosh.
my money back.
Life's not fair, Jared. Just get.
Life is
Well,
not
that's
fair.
a with balls.
right now, I'm saying no. If you don't
No,
hear
it's
from
not
me, it's a
fair.
no.
Okay. All right, so using our method here, we came up with this linear approximation. I'm not going to do all the math because for some reason my calculator got into a goofy mode. But it works out to this according to the book. I mean, we got as far as the same thing. And for the record, what is the square root of 62 degrees? Oh, that is the right answer. Come back here.
Square root of 62 degrees is approximately 1.04.
What is the sine of 62 degrees?
Sine 62 degrees is approximately 0.883.
There. This is the true answer, and that's our approximation. And they're pretty darn close. Okay? And in fact, we could have made it even a better approximation with more techniques that we're not going to learn at this exact moment. But this is pretty slick. This is a pretty slick trick of figuring out values. As long as you know the value of something nearby, you can like make an approximation there. And you like here we knew, I mean the sine and the cosine at 60 degrees are easy. What, the cosine's a half and the sine is square root of 3 over 2. Those we know. And then we were able to then make a linear approximation that's only 2 degrees of away around the unit circle, or a very, very small distance in radians. We're okay, we can make this short little linear approximation. We can assume that our function is linear over a little range, and this works just great. This is how a whole lot of forecasting works. This is actually a great and powerful thing in how the modern world works. If you have some kind of thing that you are trying to forecast, like
Air.
weather, you know I was going to weather. I can't do not anything. There. Let's make a graph of what the temperature is doing. All right. So like here's time, and here's the temperature on this axis. And you know the temperature is doing something like this. Over the, it got warmer, then it got colder. How we actually make, us meteorologists, make forecasts is at any given time here that we know the temperature, we can talk about all the different forces that are causing a change in temperature with respect to time. That's the slope of this linear approximation right here. And so for some little time in the future, some little time step in the future, might be as little as a few minutes into the future, we can know, okay, I don't know what the real curve is going to be, but I know it's going to be, we can approximate it right here. And so some short time in the future, we can make a linear approximation of what the temperature is going to be, and then we can make a linear approximation of what that temperature change is going to be to make the next step, and then make the linear approximation of what the next one is going to be, and this is how we get a forecast. Repeat that process hundreds or even thousands of times, and you have a 24-hour forecast or whatever.
Well, if you only had if you only had the morning forecast and it was just going up, how would you get it going back down?
Well, at each time, there's different, I mean, this is the trick. We got to figure out what the slope is. What are the processes causing changes in temperature with respect to time? So at like 1 o'clock in the afternoon, the temperature might be slowly going down because there's less heating from the sun. Meanwhile, the ground is giving off more of the heat to space, and so on. You have to, that's the trick, right? The devil's in the detail of figuring out that rate, or that forcing of the temperature, change in temperature with respect to time. Okay? But if at any given time you can figure this out, well, here we figured out this is the rate of change, so we'll make a linear approximation. Here's the temperature. Now we'll figure out, oh, the rate of change of temperature here is this, so that'll be our new guess as to what the temperature is going to be. At this time, maybe this is our rate of change of temperature with respect to time. When we get to over here, this is our rate of temperature change with respect to time, because of the forcings that are going on. And you have, just in a very convoluted way, discovered differential equations. And differential equations is Math 545. And you're going to actually learn how that's all done in that day, some fine day when you're doing that in a science class or an engineering class or something like that. But we're not doing that today. But we are going to hook onto that word differential for a moment. Differential equations. Differential equations is the whole business of figuring out how those kind of forecasts can be made. It's behind the scenes, which you're getting a tiny taste of today. But that word differential is something that your book gets a little hung up on. Because it wants to come up with an idea of what we mean by a differential. I mean, we've already talked about like derivatives and equations that could be differentiated, right? We could take the derivative of them, they were differentiable, which is a hard word even to say. What your book is doing with this, I don't entirely love, but I suspect it's from an application that I just don't know. They look very confident in the book when they say this, even though it looks a little scary. Remember, if you have some function, f of x, we had different ways of writing the derivative of f of x, like f prime of x, or we could talk about like derivative with respect to x of f of x. Or like, for example, if we had written the equation like y equals x squared. Well, it's not the end of the world to write that y prime equals 2x. I don't really love that tick mark notation. But another way to write it would be to say the derivative of y with respect to x equals 2x. What your book means by differentials is dy and dx. And the book tells you, okay, first off, don't think that's like a fraction, like you can cancel the d's out. It's just a notation. Okay? dy is a thing. dx is a thing. But you can treat it like with algebra, you can multiply the dx over to this side and get dy equals 2x dx. That's okay. You can move it over there like that. Okay? Just don't break the d and the x apart. Okay? It's a thing. They mean, like, this is the differential. Or like, that's, dy is the differential. This is not a notation that I've seen anyplace else. Okay? Or they might say, like, at x equals 2, if dx equals 0.1, what is dy? Okay. Well, okay, I guess I can plug this in here for x equals 2 and dx equals 0.1 and plug them in, and you'll get a value of dy. What that really means is they're saying, this slope right here that we've been talking about, that slope is dy dx. It's the derivative of y. And another way to think about it would be like, it has some slope. I mean, we could actually compute the change in y over the change in x, the rise of that function over the run of it or whatever. And so if the dx was 0.1, the dy would be some other number, let's just say something like this. Okay, well, I mean, okay. I don't love it. But it's a notation that they're going to use, and it's going to come up again. And so we're not going to skip it, okay? But I have to admit, I've never seen it done that way before. All right. This idea, though, of any equation, no matter how crazy its function is, how crazy its graph is, you can approximate little pieces of it into these linear straight lines is nice. And that's going to be helpful to you. All right. Let's go ahead and give you an assignment for this for you to get started on. Let me go pull that up. Hold on. And that is today. Let's see here. Yes. Here we are. I should actually put this in here. 3/2018. And we are on 4.2, and we are on page 364. Page 364. And we are doing problems 51 to 77 odd. All right. So there's your problem set for today. And I'm going to go ahead and start uploading the video and whatever questions you guys have or whatever. This is hugely useful stuff, and we'll make sure that everybody gets on the right page with it, okay? All right, great.